So I guess my background is Unix systems programming. I'm not really a researcher. I watch what goes on around me and I'm amazed. We've got some people with far more experience than that here today. And the purpose of this panel is to have a discussion around data-intensive workflows and extend that conversation into a definition of what might look good as we mature those concepts. I guess from what I've seen within CSIRO, workflows present the option for a new vocabulary. Workflows are a way of potentially linking disparate groups such as end users, operations teams, vendors, researchers and technical specialists, and I think that's pretty much consistent with what we've heard this morning through Gary and David's stuff. It's definitely a vocabulary that if we can get right, we can grease the rails, I guess, on our journey forward. So, Kirk, Massimo and Jake are going to do a 10-minute showcase of the workflows that they've put a lot of work into, and then Don is going to give us a brief introduction. Don was a late addition to the panel, but we welcome him, and he'll just do a brief introduction, a bit of his background, and then we'll get into the discussion.
All right, so I'm Kirk Jordan. I'm from the Data-Centric Solutions group that Yoon this morning is also from. I have the distinction of being an IBM Distinguished Engineer, which means I'm a technical executive and nobody reports to me. So unlike Yoon, he's in charge, he's a manager of a group. And then I've been spending a lot of time commuting back and forth from Boston, Massachusetts to Manchester, UK, and so I became the Chief Science Officer for IBM Research UK. I don't reside in the UK, although the Border Patrol guys are wondering. All right, so I have to, in all fairness here, explain that I once was an IBM customer, then I once was an IBM competitor. Now I work for them, and I keep telling my boss, no guarantees about tomorrow. All right, and he says the same. So, with that in mind, you know, I have always been a user of high-performance computing systems. That's what got me into this business when they were mainframes, okay? And they couldn't do the problems I needed them to do. And these computers still can't do the problems I need to do. And one of the issues now that is coming about is data's on the rise. It's been discussed already. And it comes in a variety of flavors. All right, and so what I want to just point out, I'm not going to read through this chart, but the key here is there is lots of data, and you want to do something with the data. You actually want to solve a problem. Sometimes you don't even know what problem you want to solve, but that's what it's about. And the oil and gas has traditionally been an area of high-performance computing. Then the life sciences guys got involved, and they have both data and high-performance computing needs. And then what we call high-performance analytics, HPA, which, you know, the financial industry and, you know, understanding the web, and everything else is where that comes into play. So what this all boils down to is high-performance computing and computing in general, all right? So I used to work for an oil company, and I still think that it's still a toss of a coin is almost as good as what you're going to get out of the computer to decide where you drill, okay? It's hedge your bet, but it's a big bet, so you want to hedge it as much as you can, and that's why oil companies buy high-performance computers, right? And it's to gain the insight. That's what it's really all about. You know, it still needs a human, even though we're talking about artificial intelligence, Watson, and all this other great stuff. It still needs a human to see those connections. And so we want to provide insight. So that point here is high-performance computing to give us high-performance insights. We want the business analytics and those things, but they're also being coupled with these other which have traditionally been high-performance computing areas, to get systems of insights. And that could happen in the cloud. It could happen on, your system, wherever. And where it goes from here, who knows? All right? All I know is it's changing. Oh. So we at IBM have decided, and Yoon mentioned this morning, that we had the Blue Gene system, which was a great high-performance computer. It did a lot more than most people think it did, okay, and it did it well. And what happens is we all, as those of us that work on computers, program whatever computer we have at hand, and we make it work for us to solve the problem. And if you're a researcher, whatever you have in hand, that limits what you can do for the problem, all right? So what are we doing at IBM? We decided that data is a major component of high-performance computing, and now we need to build a system that allows us to handle both data and heavy-duty floating point calculations, all right? To do that, we want to minimize the data motion because that's the expensive part of the whole machine, and even the Department of Energy doesn't want to spend lots of money on it, all right? Enable compute everywhere, so if we can put compute elements everywhere, then maybe we can do things differently, and that gets us into what the workflows are. Make it modular, so the guy at the university can teach his students on some starter kit, and then build it up so that the guys in the Department of Energy can solve their mission-critical problems. This is my little piece, to be application-driven design. And we're now changing that to be workflow-driven design, okay? Because it's going to really be a workflow, whether it's through the system or encompasses other systems feeding into it, okay? And then to keep the cost down, we want to leverage our open power efforts, okay? We've opened this up, so we want to leverage those. So moving right along, let's get into what are different types of workflows. And this is a conceptual diagram. There is no data behind this, so don't take it for what it's worth, okay? And the guy who actually put this together was lousy at PowerPoint, and so he couldn't actually put the ellipsoids together. I was the guy that put it together. All right, so there is some conceptual idea behind this, okay? So if you have data fusion with uncertainty quantification, it may involve some floating point content, but it may have more data and I/O and other things involved in it. If you're looking at traditional, how do we measure good high-performance computers, we use this LINPACK benchmark, and that's sitting down here, this little piece in the corner. It really doesn't cover the space at all that most users really want to, take over. And then there will be some things like data-intensive integer workflow that don't involve any floating point at all. And how do you build, we are a for-profit company. How do you build a system that satisfies everybody? Well, the answer is you don't. But can you satisfy enough people that you can make a profit? That's the key, right? So let's jump into some workflows. So here's a workflow. I was given a challenge when we started talking about data-centric systems and said, what if we had a workflow, okay, that was data-intensive? Do you know of any, Kirk? And I said, well, I just talked to a oil company, and they told me that their floating point content amounted to 10% of their workflow. All right, so if we really speed that up, we've done nothing for them. All right, so we now have to think of this different. And what's involved? Well, you have the acquisition data. It goes to disk. It actually comes off ships. It comes out of the ground. It's and it's messy stuff. And you have to do some pre-processing to that. And that involves going back out to storage, coming back in. What do you do, okay? And then you get into, okay, I now want to try to do the floating point content, the 3D imaging. And then after you get all that done, now I'm going to put all of this, and I've actually had the pleasure of experiencing this many times. I take all this nice simulation data, I put it onto disk, and about the time that I'm getting close to the most interesting part that I'm going to want to visualize, I filled the disk farm. Not the disk, the whole farm, all right? And as a consequence, have crashed the machine and the interesting piece I never got to, all right? So I run it again, not saving every 100th time step, but every 1,000th, all right? So that's where this comes in. And then if you're really energetic, this is the seismic piece, and then I also work in reservoir simulation, and you want to do 4D seismic, which couples the two together, boom, you've got a mess on your hands, and that's a real workflow. All right, so one other workflow I want to mention that my colleague from Unilever will actually tell you a little bit more about is we got together and said, not only do we want to make this workflow so that you get useful information out, but we need to get it out in a way that is compatible for the engineer or the scientist to take and make use of it. So we don't want to make every scientist and engineer a high-performance computing specialist. We need them to be able to make use of this as a tool. How are we doing time-wise? All right. All right, so to close my piece, all right, we're not going to, so IBM is already determined we're not going to do this alone. And where we've been working and what I've been doing and why I commute back and forth to the UK is because we're doing this in conjunction with the Science and Technology Facilities Council in the UK and their partners. And together we're doing this. So Massimo Noro will speak next, and he's one of the partners we've been working with through this the STFC at the Hartree Center. And so we made this, and what I'd like to say about this, what I want to leave you the thought here, it's not about the machines, okay? It's about building a center that has the critical mass of people that can start addressing these kinds of problems and think outside the box. All right, with that, we're going to switch to Massimo. You want to say?
Yeah, I'm just going to make a couple observations.
And you just need to click that. You want a pointer?
Yeah, thank you.
This first button.
Thanks. Can we just congratulate Kirk? That was great. And I think that just reminded me of a couple of the basic things that I've forgotten, just being able to break that workflow down to see the high-cost parts. I think that's a fantastic thing. Reproducibility, obviously, if you fill the file system up, you want to be able to rerun it without starting from scratch. But also compatibility with the end user. I think that's key moving forward. We can't expect our end users to be domain specialists. So Massimo is now going to run through a real-world commercial outcome, which is very powerful, and in which I first met Kirk and Massimo in the UK. I was very tired, but I was inspired by the things these guys were doing.
Well, thank you.
Did I get the right button?
Yeah, let's start to project
wrong,
this.
Wrong.
Yeah.
That one there. I clicked the wrong one.
Brilliant. Thank you very much, Ian, and thank you very much, Kirk, for actually setting this scene for me to actually start on. So yes, I do agree fully. It's not about the machine. It's about the people. Of course, I mean, I'm based in the northwest of the UK, in Port Sunlight, which is by Manchester. I interact very strongly with Kirk when he comes and visit. We as a company have actually signed a strategic partnership agreement with the STFC, specifically with the Hartree Center, because we have recognized that actually kind of brings together the right cohort of people, both the big facilities, the big companies like the IBMs, but also a corollary of a nice ecosystem around it. Software vendors, hardware vendors, small companies, and also data managing companies. So it is a nice package, and we wanted to buy into that. So that's why we wanted to work with them in a strategic way. And what I wanted to tell you about today is really my learnings and my challenges that I wanted to share with you when working with such an establishment, try to deliver value for my own company. And you may have not heard about Unilever as a company, but you will have heard about our brands. Of course, you will have heard about Dove, Lipton, Knorr, or Lynx. So you will have seen these bottles on the supermarket shelves when you go and do your shopping. What perhaps you don't know is how far and wide Unilever actually reach in terms of penetration of the market, because someone has actually calculated that, in fact, every day, 2 billion consumers will pick up one of our products and use it. And when you think about it, the impact numbers are staggering. So I'm working on a new version of the shampoo. 3 months down the line, 2 billion people might be actually picking that up and then wash their hair with it. It's absolutely inspiring, because you can do a lot of good, in this way. And of course, we sell our products throughout the world in 180 countries, but in fact, most of our sales come from the emerging markets, countries like Brazil, India, Indonesia, China. This is really where the new actually markets are going. And I have to share that, in fact, inventing, developing, making and selling a shampoo or a soap is more complicated than one might actually think, because we have a variety of lines throughout the world with local variations. We need to deal with different raw materials coming in. And if you do the sums, the complexity of managing such a number of SKUs becomes comparable to actually dealing with the elements of a typical Boeing 747, which is an incredible complexity. So again, we have to find ways to manage our R&D processes with workflows that allow us to keep track of every single ingredient that we have and every single process. This is why we need to embrace that, and we have done that. So what do we do? Well, this is our typical workflow. We always start from the consumer. So we always start from trying to anticipate what the consumer needs are. So the consumer might want to have smoother hair or more curly hair. And then we need to translate this consumer benefit into, well, too late for me, because I've got no more hair and gray. But of course, some of my colleagues, well, not even Kirk, I think that's probably wasted on him. But, some of us still have these needs. And so we need to translate that consumer need into a technical target. So which is that molecule that we can put into a new formulation that actually deliver that benefit? So we try to translate that into a technical target. What are the scientific criteria to do that? And we try and run a series of tests so that we can actually screen for or invent that new molecule that actually deliver the benefits. We have to test for the efficacy. We need to match a number of criteria as well. So this molecule needs to satisfy, for example, regulatory toxicity tests, and we are very, very stringent on that. Of course, we have to go around this, and of course, we have to worry about IP protection, patentability, where it comes from. So we go around this loop once, twice, 3 times. What if, in fact, we can accelerate this by adding an element of high-performance computing? And this is what exactly we have done, thanks to Kirk, thanks to this partnership with the Hartree Center. So we brought together, really, our knowledge on how to do the R&D cycle together with the power of defining this workflow so that we could add the high-performance computing element to this and get to that solution a lot faster. In the end, we want a molecule that we can put in a bottle. This is really our deliverable, and we want to minimize time to achievement that. We want to really minimize that. Well, in practice, we were able to actually share much of our own IP on how to simulate how water, surfactant, and polymers come together to make that liquid structure that goes into a bottle. We ran those simulations on a code optimized for the blue gene running at the Hartree Center. And not happy with that, we also worked with Kirk and his team to actually put a friendly interface, because this is not something for me to use just. It is actually something that I want to hand over to my colleagues down the hall who are the real formulators, because they themselves need to think outside the box, need to really explore all spaces, all space of possibilities, changing the ratio between the ingredients so that we can actually match that consumer need that we started with. So the outcome really was a power supercomputer on the palm of your hand in a way that you can just move your finger up and down and then try in different scenarios. So why? Of course, because this, kind of getting to market first, doing this faster, has a huge implication from the market side. And this is data that, in fact, it is not just Unilever. This is data that was reported by the Boston Consulting Group in 2012, going across the whole cohort of FMCG, fast-moving consumer goods company. Well, typically, a new product is launched within 22 months, from the R&D processes. But if you are the best in class within this cohort, then you're able to launch 7 months earlier. So shave off 7 months. That 7 months earlier, if they're on the critical path, actually translates, they say, because they've done all the sums, into an increase in 60% of sales in the first year. Now, if you're selling shampoo in 180 countries and then 2 billion people use it once a day, that's a big number in terms of the outcome. So get into solution first, really get into that, using the proper workflow and optimizing for that has a huge impact, not just for us, but for many companies like us. Let me also finish off with a couple of slides, please, Ian. So the first one is about our formulation journey. So this is how we started. Well, at the turn of the last century, this is what our people were doing. They were working on a bench, much like that, when Bill Lever started Unilever as a company. And they were able to actually try perhaps one full formulation, 2 or 3 per day. Very, very low turnout. But in the middle, say, of the beginning of the century, 1900, this is the typical lab space. And again, still manual, but you've optimized the processes, and you would actually churn out about 5 to 7 formulations per day, full liter. We actually, in the 90s, moved on to the high throughput machines. And now with that, of course, you add what Ian was talking about, reproducibility, because in this way you have to specify again a workflow that will actually reproduce the same process and the same quality of the sample over and over and over again, which is a great achievement already. And not only do you get the reproducibility, but also increasing throughput. Well, this is all fully automated, and you get to about 25 per day, which is already a great result. But the next step, really, when you really want to expand the space of possibilities, you want to explore almost everything, right, is to go digital. We call it in silico, right? And our ambition is really to do a first screening silico and then find out where the leads are, the pockets, or exclude areas of diffuse possibility, and then just focusing on that. Now, that way, we can actually explore every day something like thousands and thousands of different possibilities, and of course, focus in, and then just do perhaps this work or that work, only where it matters. Of course, you have to do the experiment. You have to be sure that everything works, but you can do a lot more before that through this visual workflow. And I'll finish with one real example, which is what we did a couple of years ago, again, embracing this workflow, and we have really drastically reduced our time to market, inventing a new polymer. In the first quarter of 2013, this is when we first through this high throughput campaign, found that a new polymer, polymer X, let's call it. I cannot reveal the name of this, otherwise my chief executive will shoot me on the spot. In partnership with the Liverpool University. Soon after, it was actually shared with one of our suppliers. So they started actually scaling up from 1 gram to about 2 to 30 grams to do all the development work. And when that was actually kind of optimized, we actually went onto the final scale pilot trial at Dow in quarter 2 of 2014. They made the commercial first batch, about 50,000 kilograms, into factory, and quarter 1 2015 it was implemented into a flagship liquid product that we have, to the tune of 5,000 tons per year. Now, going from 1 gram to 5,000 tons, again, that was a long journey. This is real workflow. But then we were able to shorten that thanks to really doing things first in silico and then on a high throughput machine. So what are the opportunities for a company like us? So these are 5 examples of workflows, and this is things that we are working already on or that we would like to work on. So first of all, I think that we already mentioned the idea of the computer-aided formulation, how to predict through a classic simulation when water, surfactant, and polymer come together to make that liquid structure. 2, once we know what we want, we can actually optimize the ratio of the ingredients in there through classic optimization type of theories. But also, there is a key thing there in trying to how do you process things up? How do you scale up from this scale to ton scale? And that's called the processing type of step, which can be done in silico through typical fluid dynamics type of calculation, but also you could also try and virtualize how you design a bottle. Again, that again can be done with CAD type studies. And last but not least, when you are in the factory, you can try and optimize the productivity of that factory. So 5 examples, 5 different workflows, which we are working on, in fact, together with our friends at Hartree Center. And just because we found there this nice convergence of interest, both the new science, new technology, new computer, in this nice ecosystem. But I'll stop here, because then I know that we're running out of time, and then we want to save time for the discussion. Thank you.
Thanks very much, Massimo. That was great. So Jake is from the Queensland Brain Institute, where he tells me they do all sorts of interesting experiments on brains. Quite disturbing, really. Anyway.
Right, so, a little bit dark. We won't go too much into an introduction. I'll just say, yep, that's where I'm from. I think there's a couple of people in the audience that know who I am. I know a couple of you. Anyway, so what is QBI? The Brain Institute is probably the largest and most computationally and storage aggressive neuroscience research-focused institute in the world. It's a fun place to work. It feels like Big Bang Theory most days. Labs are dedicated to understanding the fundamental mechanisms that regulate brain function. In a mouthful, what have we done recently? We discovered the amygdaloid plaque and the protein to potentially reverse Alzheimer's. Right? That made the Wall Street Journal, amongst other things, if no one noticed. It's a pretty big deal. So we're working to solve probably what you would consider some of humanity's greatest problems as far as neural degeneration is concerned. So what we're doing, in my opinion at least, matters. So we're an early adopter of technology in general. We are the crazy ones, you might say. We break things, vendors give us things, we destroy them, and we give them back. And they say, oh, look at that, it failed in new and exciting ways. So that's it's a good thing. Why am I here? I came to learn primarily. It's a really cool audience. There's some great people here, there's a wealth of experience. And I think it's these kinds of boutique conferences which I'm kind of attracted to lately. So anyway, I came to show you how workflows matter to us in the same way that Kirk has, and in the same way that Massimo has as well, and a little bit to exemplify exactly what Ian Corner is getting at. So I thought I came to discuss as well how we can revolutionise this stuff together, in a sense. I think with all these people in the room, there's a real opportunity to change things for the better. So what types of science drive our workloads? Well, there's basic biology. I call that the boring stuff. There's computational neuroscience. There's complex trait genomics. If you know what next generation sequencing is, this is a level beyond it, and it will frighten you if you ever see the data outputs. There's electrophysiology, and there's cognitive neuroscience, right? Computational biology. So what does QBI want with workflows? Well, traditional beginnings, really. We had big supers, big storage, significant complexity, clever people doing clever things to find clever answers to complex problems in theory. Turns out biologists don't really have the time to learn the ins and outs of parallel file systems and how our job schedulers work. It's not what they're into, funnily enough. So, you know, we had to kind of learn to work with that. They just want to get their work done, and they want to get publishable outputs, right? So every aspect of the scientific life in the lab is expressed in silico in some way, in a workflow, we believe. And I think that kind of rings true in kind of what Ian said before about the birth, deaths and marriages register of how a workflow might work or how a piece of data might be, you know, in a life. So there's 2 types of users, really, in our opinion. The first is this guy. He is a wet lab scientist, okay? And the second is this guy. He's not a wet lab scientist. I hope everybody knows who that is. It's Turing, if no one. Anyway, so it's like joke falls flat. So joke falls completely flat. Anyway, so guess who has more sophisticated needs, right? Hint: it's not the computer scientist. The most sophisticated person in the room is not the computer scientist. It's the person on the left. He is our user, and he is our person who is gold to us. He is the person who picks up his iPad at the end of the day and says, I need to be able to do this and I need to be able to do it now. Find me a way to achieve that by pressing one button. That is a far more complex and far more sophisticated set of things that have to take place under the surface than a computer scientist sitting there, minding his own business, cutting assembly, okay? So people still do that, as it turns out. So anyway, I think that exemplifies a bit of a use case, right? So how are we helping our people? Well, we're building pipelines and workflow engines. So there's a pipeline and a workflow engine in very, very dark. Can we turn the lights down? Is there a way to turn the lights down? So anyway, that's a workflow engine we're using in microscopy at the moment, and you'll see that exemplified in a moment. But we're building tools to get data up and out and to the right locations, harvesting metadata along the way. Right? People without HPC backgrounds really only peripherally appreciate the difference between scratch storage, campaign space, or archival storage. People back home don't even know what campaign storage is, right? So at the end of the day, there shouldn't really be a need for them to worry about any of this, where a workflow will cover for the job, right? So when we build, we're not building anymore for IOPS or crazy throughput. We're not even thinking about those things first. We're building for the workflow, right? So here's an image deconvolution workflow, and it's a shame that it is so bright in here because you'd get to see a whole bunch of cool fluorescent microscopy behind the scenes otherwise. I know at least one person here that knows what fluorescent microscopy is. So anyway, what is deconvolution? Let's talk about that. Deconvolution is a mathematical operation. It restores and recovers objects in an image that have been degraded, and usually it's photonically induced, that degradation. It's a whole bunch of interesting effects that occur when you start to observe photons at a very, very low level. Things don't behave the way they should, so you use algorithms to fix them. Right. That's a little bit better. Thanks. Appreciate it. Our version of this runs on GPUs, okay? NVIDIA K80s. If there's anyone from NVIDIA in the room, I really would like a P100 or a few, please. You won't let me near them currently. So I'm sure there's some people in the room who have them already. So anyway, the principle behind it is by a guy named Huygens. He was a 16th century physicist and mathematician, hell of a guy. And you get an idea of what happens when you're sitting at an objective lens space and photons bounce around, you get a wave front, and something like that happens. I won't go into the physics and the detail. I need my microscopy guy next to me to explain it properly. I can't do it justice. So, to give you an example of kind of what happens or what it looks like, and let's hope it comes out okay. Oh yeah, there we go. So, this is that's a neuronal cyst which has not been deconvolved. This is what it will look like if we deconvolve it. I'm hoping you can see the difference in clarity between the two. Now, the interesting point in this workflow is how hard it is to do. So that's 5 gigabytes a second of PCIe bandwidth across a board for about 1 hour. There's 86 billion neurons, as we understand it, in a human brain, right? We're doing this, on several of these things every day. It's hard work, okay? This is heavy stuff. This is on single neuronal imaging, right? So our workflow looks like this. We acquire the data from the scope. It is rich in metadata, okay? The uploader gathers most of the metadata, dumps it out as a POSIX object at that point in time with all the metadata attached into a back end, like the Noro environment, the open microscopy environment. And we then automatically throw it to a deconvolution pipeline with a fairly serious bit of GPU and HPC infrastructure. We store it in Ceph. We are using the Rados block provider at the top there, using OpenStack. We throw it out there, we put it back, it's deconvolved, back and forth. Then we send it out to HSM, okay? And we put it into a large data store somewhere. So flash, disk, and tape. Now this is all transparent to the end user, as it should be. Users should not worry about these things. It's all sent out to the repository after that, okay? We send the metadata up and out. So what's the repository look like? Well, this is the cool bit. It's a massive multi-domain workflow and workload metadata consolidated engine in a DB, okay? DICOM and human data, NGS, high resolution, super resolution microscopy, ePhys and deep brain stimulation. DBS, if anybody's interested, is actually when you shock things. If you know anything about that, it's a pretty interesting and unusual field. My boss, he's an electrophysiologist. He used to shock himself before he shocked other things. That's interesting. Yeah, that's what electrophysiologists do. And in the middle is the coolest part of all. We have a multi-petabyte. Oh, one sec, sorry. Oh, that's not fun. There we go. Here it comes. Yeah. There we go. And again, it's a bioinformatics repository effectively, and what it allows us to do is create great cross-correlation between all of those kinds of workloads and all of those bits of science that are taking place so that we can actually learn from what we've done. And an example of what Ian Corner said earlier about not losing lessons, about not losing the data at inception, is that we're going to go back to this stuff. Every week in genomics, we make a leap forward in terms of the algorithm that is used to generate things, right? We're going to go back to data which is 4 or 5 years old and going to go, oh, you know what? That really wasn't right. In fact, the algorithms were way off. Wow, that data meant nothing. We probably should reanalyze it. Well, how much did that cost? So this is part of the reason why all this stuff matters. But things are getting worse. We've got 100,000 by 100,000 cyst pixel image, 100,000 by 100,000 pixel cyst image here in 3D deconvolved reconstruction. It's about 4 terabytes in size, this particular image. And we're dealing with, a few hundred of those a day. It's hard work. So things aren't getting better. Budgets are getting squished. I'm sure it's the same with the NSF. It's the same in our country with the ARC and NHMRC. Life's getting hard, right? So takeaways in this bit, please stop thinking monolithically. Think about patterns and use case modularity. There's no better time now than to start embedding hints in file system design so that we can carry things up and out of file systems and give more rich metadata. Ian said before, we have very, very little hope with POSIX at this stage about getting anything rich out of it anymore. Build me a storage subsystem that's aware of locality, compute workloads, I/O patterns, and personas. I'd love to see that. And how cool would a fresh and reasonable data locality mechanism be in an interface definition language that would allow us to do something like that? And I don't mean DynMappy, okay? So that'd be really nice. And some takeaways. I guess cross-domain scientific research really pours huge metadata at us. It's great for indexability, discoverability, and reuse. We've got to get to it though. Don't lose the lessons. Correlation and reanalysis is a big deal. It's going to be the thing that we eventually look back on in a few years and go, yep, you know what, we can cure that now. And I guess information flow. Without information flow and without a mechanism or an underlying architecture to deal with this stuff, we've got nothing. Okay, so I'll just say that. Starts here, and can we count you in? Because I need the buy-in, ultimately, of the big iron vendors, the software companies, and everybody in between to create something cohesive here. We can't do it alone, I don't think, and we certainly can't commoditize it. And for those that do end up on the front foot, you have a multi-billion-dollar industry on your hands, I promise you. Thank you.
So, Don's just going to give us a quick 30-second intro. Don is a late addition to the panel, and thanks very much.
So, thanks very much. Thanks for having me on. I know a bunch of you from here. Until recently, I had a different hat. So until I'm counting it in, I just changed from weeks to months. Until 3 months ago, I had been at the National Institutes of Health, one of the national labs, NCBI, and I was responsible for a lot of the genomics infrastructure, a lot of the big data infrastructure that we talked about here. Previous to that, I'd been working in neuroimaging as well, so I've been doing big data workflows for a long time. Build the infrastructure for this. I'd been CTO at the NIH as well, and been speaking actually with Jacob Farmer, who's over here, for a number of years about a project he'd been working on called Starfish, which actually did a lot of the same things that we were doing at NIH. And so every time he came by to talk to me, I'd say, I've got that already, I don't need it. Well, one of the reasons for that is people kept asking me for my software when we were developing software at the NIH, and we couldn't give it to them because it was so glued in to everything else we did. But it included all of the workflows, it included databases, metadata. So when the opportunity came up, I made the changeover, and I'm over now at Starfish Storage and working on building a lot of the same products that we had done already, working on research lifecycle for large computing. People have petabytes of data, billions of files, metadata-driven, a lot of the things that you heard Ian speak about earlier and some of the other folks speaking about where POSIX file systems don't do quite enough anymore, and you need something else to go along with it. Well, we think we provide something else, but mostly I'm here to talk about the data workflows and join in the conversation.
Thanks very much. That was great. So we're pretty flexible in how we go about this. So I'm going to just put some questions up on the screen. Workflows are sort of new to some people. They're not so new to others. We've had a great variation in different workflows. workflows to keep you clean, workflows to save your life, and workflows to find oil. So, the question here is, do workflows act as a vocabulary to help us communicate across domains and help us get to a solution in a shorter period of time? If there's anyone from the audience or anyone in the panel, I think the panel's going to agree. Thoughts?
So I'll start off with this. So as I pointed out, I was looking at a data-intensive workflow that just happened to look for oil. That data-intensive workflow could have equally have been what Jake talked about, or it could have been equally the same thing as what Massimo mentioned. And the thing is, and what I need to go back to IBM with is, here's an abstraction that allows me to say this kind of workflow has this kind of characteristics, and this impacts the way we design machines so that we build better machines for the end user, of which I consider myself one.
So I think that's particularly pertinent, and if you can actually start to think about silicon again in a more customized way, I think we're actually going to see a little bit of a renaissance. And we, I saw it last year at SC a little bit. We're starting to see proliferation of specific silicon for specific workloads again. I know commodity exists, but I agree with you entirely that this might benefit this entire industry if we can do that.
So just on that, Jake, you mentioned that the neuron takes an hour at 5.6
bytes a
second,
yeah.
right?
Yeah.
And there's 80 billion...
83 billion, roughly.
83 billion, so there's a long way to go in terms of real-time imaging of the human brain.
Yeah, and that's exactly where we're at. We're at whole-of-brain imaging at this
point. Yeah, so that's a big backlog of computing, and then the possibility of optimising that and taking it out to the world has probably got a whole lot of value.
Right, there's a neurobiologist at Harvard that we've been speaking with who's working on a 1 cubic millimeter.
Turn around.
Sorry, 1 cubic millimeter of a brain, and that's going to generate 300 million images and require all of this compute, put it back as a mosaic. He just had an article published in Nature about it if you're interested, because both from a strict mechanical and electrical engineering basis, creating a scanning electron microscope with 63 parallel inputs, but also from the computer science, the storage side of it, he's doing just some amazing work. And so, that's one of those cases where you want to capture the information right at the source of generation, capture the provenance, capture some additional metadata that might not be available in the files later on, and perhaps it's as simple as X, Y, and Z access, right? But that then feeds everything else from, again, from point of birth all the way through.
Can I add two thoughts to this?
Okay.
The first one is that, yes, of course, I totally agree with this. What really matters to us in our industry is time to solution. It doesn't matter how you get there. It doesn't matter if I have to use a PC, a laptop, or a supercomputer. What really matters to us is really getting there first. So this is thought number one. Thought number two is never underestimate the power of something which is user-friendly. And let me just share with you what we did for the end of the workflow when it was to deliver the iPad app. We really called up a group of 7 naive users, 7 people that are wet chemists, and we just gave them literally a white piece of paper. I said, what would you like to see? What questions would you like to ask? And what language would you want to have there? Would you want this to be expressed in grams or in moles or in percentages? So tell me what language you use when you go into the lab, because then we will actually design for you this app, which you will use, not I, you will use. So you have to decide what you want. And that really kind of having this engagement with the end user, people that will use that really makes all the difference.
That's interesting, because I got that out of your presentation, Jake. It's really very much from the beginning of the imagery process to delivering it in a coherent, metadata-rich environment. Cool. So I guess the obvious follow-on from this morning's panel was, are there things that you wish you could do, that you could articulate in a workflow today that we can't actually do because the infrastructure doesn't exist, or it's not fast enough, or it's too expensive? Are there potential things in the workflow? I suppose that's a Jake question, unless Unilever's planning to take over the world. Or
Well, they might be, you never know.
conquering the world with soap.
I think currently, for us, throughput is a significant problem in any workflow we create. And that's a derivation of the fact that we simply don't have the infrastructure scale in the physical capacity or space to be able to attain what we need to attain. We don't have many hundreds of thousands of foot of data center space to achieve that. I believe denser packed application-specific technologies are going to be the way forward. So, hardware ASICs have their place, acceleration hardware has its place, and I think that will enable workloads that we dream of, as in real time.
So in terms of scale beyond where you are at the moment, is that 10 times faster? Is it 1,000 times faster?
It's a 10 times faster proposition.
Yep.
That's what it is.
But that'll get you to a point where you can see you can do more things, and then you'll want another 10 times, won't you?
Absolutely, yeah.
Okay, so the next question around this, and is there any thoughts from the audience at this point? Otherwise, I'm happy to keep going through our stuff. I got a few things out of this morning around whether workflows were really a practical way of articulating application behaviour. I think Lance mentioned that once you get into the details of the application, you find a whole lot of nuances and stuff that break it all apart. I guess my counterpoint to that is we've sort of set boundary conditions. As long as we can make the step in the workflow, 2 to 5 times faster, the researcher's pretty happy, and we move on to the next workflow. And so we've been able to have this sort of containerised approach that avoids getting into too much detail while still getting a benefit. Is that something that's common? Is that an experience that people are familiar with, or do I just have the luck of working with 4,000 research projects that happen to be almost identical? Thoughts?
I can take a bit of that. So one of the things that we'd done when we were starting to work on some things at NCBI was we went around and looked for workflow systems. And what we'd found actually was that there were quite a few out there, but they tended to either be very flexible, in which case they were difficult to work with, or they were very specific, which meant they were too specific for our purposes. And so we wound up creating our own, right? Everyone does, right? It's the this is too hot, this is too cold, do just right. But we wound up creating our own domain-specific workflow system because it could meet those needs. But that's what then allowed us to work more closely in the genomics area. So I think one of the things we may find is that we may need domain-specific workflow systems. They might be generalizable at a very high level, and then as we get in further, we'll need domain-specific folks to work on them, subject matter folks to extend them out into their areas.
So, sorry, Don, from memory, you've had experience with Galaxy.
Yep.
So does that do that? Does Galaxy support that sort of agnostic view at the top, and then as you get further down, you get into the...
It does. So for those who aren't familiar, Galaxy is it actually started from genomics workflow, and it is a web-friendly tool that basically wraps command line applications, but lets you tie them together, gives you a workflow application to build up workflow graphs. And so that does let you do some of that, lets you tie in some external commands, lets you tie outputs of one into the inputs of the other. And that's good. One of the interesting problems with it, and I'm not sure if there's a good way to express this in any of the workflow systems, which is one of the reasons why we had to do things, and it came up in Kirk's talk, was the need to minimize data movement, right? So especially if you're working in genomics, if you're working in any of the large data files, what you really don't want to do is have a pipe type system where you're piping data from one application to the next, to the next, to the next. Each of those copies is very expensive. So one of the things we had done was we wanted to do a plugin architecture where files would be read, they'd be put into a buffer, many things could process that buffer and move on. And that one itself was just a very quick speed up. Just on a slightly different note, one of the other things was at at a meeting that the ESNet folks at DOE were very nice to invite me to. And one of the things they do is they have an annual review of a variety of projects that they have. And this is very useful because they can find out what's coming up. People can discuss the projects. One of the things they also do is they invite mathematicians in. So there's a group of mathematicians at Berkeley that work very closely with them. And that was a huge win. All right? They're able to sit down, and mathematicians, we've got computer scientists, we've got biologists. Mathematicians think about these things as well in very different ways. And they were able to bring their knowledge and skills and algorithms from a variety of different areas and provide those 10x, 100x speedups for no additional compute. They were able to just speed things up. So if you have the capability of including some of those, you may want to look into it. All right, algorithms may, changing an algorithm, pulling something in that might be from physics into biology could be a big win.
Yeah, and so we see that in our organisation. There's a lot of cross-domain involvement in workflows that you might not expect people to be involved in. So are you saying that they took an existing workflow task within the context of the workflow, rewrote it, and just put it in as a replacement?
Yep. So they were able to find that critical area in the task and provide that huge speed up.
And within Galaxy, can you see what is costing you with the workflow? I mean, can you do the top 10 workflows, and then within those top 10 workflows look at the...
I don't believe so.
Do you think that'd be an advantage?
It would be.
Yep. Okay, so I guess this slide is around can we rethink our industry challenges as workflow problems? So can I just have a show of hands around people who've come here today and think that workflows might have a future in helping us optimise work or communicate better within the IT industry? Is there any... Wow. What do you think of that, Matthew? Do I get a commission on that? Is that how that works? There's a lot of people. So say we prove this was successful, do you think there would be even more involvement? I mean, so at the moment there might be some people doubting there. Is there anyone who thinks that if there was more information or a few more success stories, can I have a show of hands that would believe then? Yeah? Yep, more believers, good. Okay, so I guess that leads us to the next question, which is...
So I have a quick question.
Oh yeah,
about
good.
That. The workflows you're automating and you're approaching, are they new? They're existing workflows that you're essentially automating. Do you see any movement towards new and more interesting things? One of the things about going faster at doing something is that presumably some smart researcher looks at it and says, because I can go faster, I can go do something different. Are you seeing that already, or is it strictly just doing what I've been doing before but doing it faster?
So I'm sure we've all got an answer on this. For us at least, it wasn't necessarily about going faster, because in this particular case, we could go at the same speed except in monolithic blocks. The reason we put these workflows together to begin with was a function of usability more than anything. Just to be clear, if we were to apply it to a new thing, which is not an existing set of processes, it would be primarily for usability and ease of access to our users, and not in the first instance for speed. That's just my own organisation though.
So I'll comment. One of the reasons I'm very interested in the workflows is you start with the sort of the traditional workflows, but now can we rearrange them, like what Massimo was saying? Time to solution is the key issue. I know that if I could change the seismic survey, which takes roughly about 18 months to do, and do it in 15 months, the oil industry will be knocking on IBM's door to buy that system. All right. If I can make it in 12 months, I won't even have to even tell them. They will be coming in, and my bosses will be extremely happy. Of course, then they'll probably promote me, and I'll have more problems. But the thing is, it's really time to solution. I don't care how fast the machine goes. I've never cared how fast the machine goes. I care, can I actually solve the problem? I learned this as when I was first out in a company that had a problem. They wanted it solved. It took me 3 years to get there, and there were about 6 PhD theses that came out of that and are still coming out of that, and I wrote one paper on it, but be that as it may, And that was because I am a mathematician, and we changed the mathematics. So my hope is that we will discover new ways to do things faster and better and more accurately. And I think that's what, there's an opportunity here that the computing industry has given you all the speed it can give you for floating point. And we're not going to give you much more. So that's it, right? So now, and that's not our problem anyway, okay? The problem is we got to move that data around. That's what's taking all the electricity to do it, all the power and cooling and everything. And in fact, even just to keep the memory sort of available so you could use it is still, so even if you don't do anything with the computer, the memory is costing you all the power and cooling and everything, even if you don't put anything in it. So, if we can change the whole concept, maybe we solve different problems and we solve important problems that have an impact and get solutions sooner. So that's sort of my take on it and why I'm really interested in why right now the application or workflow-driven piece of this, because I don't believe we at IBM understand what that means yet. So we're still looking, and we're not going to do it by ourselves. We're going to do it with our partners. Did you want to add?
Yeah, I just wanted to add just one more concept to it, which is, yes, faster is good, but better is actually the other component. So again, one of the things that I tried to say before is that if you have access to a workflow system and then you can do things in silico, you can explore much more of the space of possibilities, which otherwise you wouldn't. So suppose that you have, a formulation with 15 ingredients in it, and you decided you want to scope, 5 points initial ingredients. You work out the number of experiments you have to do through the. It comes out to 31 billion. It's incredible. So if you were to put a team onto it, you would have to start, at the beginning of times to do things until now, which is not possible, right? But then if you articulate that in a workflow system, and then you can really do an experimental design, so you don't miss out on anything. So you don't miss out on these pockets, which otherwise you wouldn't have looked at. So I think it is, yes, faster, but also better, because it allows you to space out a bit more onto all the area of possibilities.
Cool. So I think that leads into the next point. I think we're defining success here, and it looks like we're doing things faster, which we all want to do, but we're also not missing out on opportunities. And I think one of the things that Unilever spoke to me, their approach spoke to me about, was they were balancing the environmental impact, benefiting the community while also making a profit. And I think that is trading off three competing interests. And I think that's a really important place for us to be in the future. Sorry, yep, sir?
So a comment and one question. The comment is, with data-intensive workflows or data workflows, I think you have to be careful in how you precisely define this, because there's been a lot of computing paradigms like utility computing and, to a certain degree, cloud computing and this computing and that computing, and some of them have been more successful than others, but some of them never took off really well, generally speaking. Mm-hmm. Mm-hmm. So I think you have to really well define what you mean by data workflow. I think most of the people in this room, based on this discussion and the earlier panel, have an idea, but the wider community, computationally and storage speaking. So that's the comment.
That's good.
The question
Thanks
is,
very much.
It's not so much time to solution that you want to drive to. That's important. But I think IBM's approach with programs like Watson is more to be automated exploration of solution space, to basically postulate questions that you don't know you need to ask, right? Yeah. So that needs to be part of this as well, because you have tremendous computational capability, more than you did 10 or 15 years ago. Yeah. But I think you need to have that factored in here as well.
So that I'd agree, and that is exactly why that whole grouping of metadata, provenance and semantics into an interface that's consumable, because that's one of the blockers to machine learning. You've got to teach the machine how to access the data. Now, if we can get our data sets to be presented through a consistent interface, and those data sets grow from 0 to 360 like they did in the last 4 years, and they're now doubling every year, then within a few years we've got massive domain-specific data sets that could be trawled. Yeah, but you've got to know how to talk to them, and I think the only way we can scale that is having a consistent interface.
So my question for the panel is, how do they see that evolving in, say, the next 5 to 10 years? I know it's, give me your best swag.
So actually, we're already we're starting down that path, because what we started to do with the STFC in the UK was we didn't talk about data-centric computing. We talked about data-centric cognitive computing. Massimo was part of the inspiration behind this, because the original formulation, computer-aided formulation, involved a colleague of ours at STFC at Daresbury Labs spending months working through the parameterization, and we said, what if we could do that faster by using machine learning, because it was a training process that we had to sort of train the person and the machine and everything, and we actually just implemented that in the last 2 months, and it's kind of working already, and so we're exploring that. And then that really puts the thousands of in silico experiments in the hands of the formulation chemists, the wet lab chemists, because it's all packaged together as an entire workflow, and then they can start playing the what-if games to get through that 1,000 very quickly and understand which are the ones that they need to go put into the lab. I know you want to say more about that.
Well, I would like to add one more concept to it. So thanks for explaining that. I mean, I cannot add anything more to that. The other thing I want to add is really the concept of validation and reproducibility. Because, I mean, in the end, data is just data, whether it comes from a simulation or whether it comes from a real experiment. And really what we have been trying to do is to overlay the two and make sure that the simulation gives the proper data that fits the same phase diagram or formulation that actually you can measure through a high throughput type of experiments. When that is the case, then your data set really expands, because you can merge your simulation data, your real data, and you can treat it just as data. And of course, at that point, you can play the game of adding cognitive computing or machine learning to just work on that. And I think that really kind of that speaks to, one, is validation, and two, reproducibility, the other big concept that I think that we have to worry about.
Cool. Okay, so I think Matthew wants to ask a question, and then that's probably time up.
Yeah. Well, actually, actually make a comment really to success. What does that look like? So I think when I first met you in Australia and then invited you to speak, I think what struck me about the kind of what the vision you're working on is kind of, it's very comprehensive. So it's really end to end, all the way from, okay, what is this data? Like you said, we birth it, we validate it, we clean it, we make sure it's calibrated. And then we have ways of abstracting how it flows through the infrastructure so that we can communicate down to the infrastructure what we need, can communicate up to users how they should think of it, and then not just single per user, but organizationally, right? We can scale it across. So I guess the thing that struck me is this, I'm old enough to have worked within this community for several decades or more. And there have been times where this community has come together and done things like the mass storage system reference model. So some of you might be old enough to remember that was basically the centers all had the same problem. They couldn't get the vendors to build systems big enough for them. So a lot of them built their own HSMs, and they had a model that could kind of help them understand abstraction that worked well within that framework, like third-party data transfer. And I think for the time, that was a big advancement, and that was a great, I think, a good theme for the community. So, fast forward 20 years, we do have, we see, for example, our speaker this morning, we have just amazing amounts of IOPS and performance. We have, my colleague April from Storage Tech will be telling us, 10 terabyte tape drives. It's not that that's enough yet, but the truth is we're getting some of these physical problems solved, and we've kind of neglected these it's always fun to work on the engines and making stuff super fast, and so these abstractions but I think these abstractions are powerful. They may not be exactly the correct ones, but they seem like a starting point. Mm-hmm. So for me, what success looks like is we start a conversation where other, Gary and the team at Los Alamos and other labs are doing workflows specifically for RFPs and kind of a computational emphasis, but frankly, they sort of fit within your data model in my mind. In other words, it's actually fairly complementary. But so anyway, the net of it is a success to me looks like you get a lot of conversations, people talking to you, folks like Francis DeCane from ECMWF. We have other folks in big centers. We start talking and maybe CSIRO shares code. Maybe you have regular 6-month workshops, that kind of thing. So that's what I'm thinking. So I'd love to hear your response and hear what the panel members think.
So just one last thing I'd add to that, Matthew. Maybe it is time that industry kind of looked at this in a different light and thought that it is time for a new definition language. It is time to look at interfaces in a different light, as we looked at SCSI before I was born, as we looked at the TCP/IP stack as it evolved, as we looked at fibre channel. Maybe it's time for architecture to take another look at the definition language we use for these things, so that customization in each domain or field can actually have some structure underneath it. That is a suggestion I would posit. And there's people here who have the ability to actually enact that kind of change, I believe. So.
Well, the other thing is I think what you've been successful at is communicating up to your users the way they should think about the infrastructure. And part of that's kind of you're Jay Carroll and you're good at it, but you have a bunch of, it's like you said, it's this way of thinking that becomes a powerful way to describe what we do, IT services we provide, and then build behind them. So
yeah. I think there's a lot in all of that. First of all, there's a vocabulary that I think workflows are, which start a discussion.
Absolutely.
There's the TCP/IP layers that, and it was always inevitable that IPI drives and VME disks, it was always inevitable they were going to fail. So, so we've got the history there. And we're currently putting together the definition of a proof of concept around this. Okay. I don't see this as a short game. I'd say that in 5 years' time we'll know where we should be going, but we're definitely keen to partner and collaborate with anyone that's willing, and regardless we'll be going down this path ourselves anyway because we see it as very necessary. I think we've been having discussions particularly with the panel members previously, and so I think that's a great suggestion, and it would definitely define success, or at least get us to a point where we could be successful. So.
I agree. I think researchers, in your presentation you pointed out as well, they'd like to deal with the data as a higher level concept. They don't want to deal with 70,000 files or 530 million files that are involved with a project. They want to deal with the project. And the other thing that they do note, again, as in your presentation, there's some data that's the ingest data, there's some data that's scratch data, there's some data that's validation, and they may not need any of that once they've reached the last point. But again, what they'd like to be able to say is, okay, I've hit the end of this workflow. You can get rid of all of this stuff in the middle. I've got the stuff at the beginning, put the stuff at the end out on publication, and we're done. Yeah. And that's the concept level they want to deal with. And oh, by the way, on the other side, curators may want to come along because maybe this data also has some lifetime and should only be out there for 7 years, and somebody else needs to keep track of that.
Yeah. All right. Okay, at that, if there's no more questions, then I think...
One more. Okay, one more.
I said no more questions.
I promise this is a good one. So it was good to hear the comment on cloud computing, but I didn't see anyone jump on that because this feels like cloud computing, especially with folks wanting to put HPC apps into the cloud and scale out as far as they want to go. In terms of describing workflows, cloud folks make their users describe inputs, outputs, compute elements, dependencies, and all of that. So it feels like there's something here that can be exploited, and these two worlds can come together.
Absolutely, I agree. It's not that we're proposing new stuff. here. I mean, there's, like I was saying, we've got plenty of people doing the whole provenance thing, but it's painful and it's cobbled together. It's not that we haven't been able to pipe things together or plug them together. There's, tools like Galaxy are doing it. It's about taking those good things that are all there, and then let's look at what general looks like, what's good on a general sense, and then the TCP/IP model. It's stacked. The higher you go up the stack, the more information is there. And I think out of that, you probably get exactly what you're saying. You get the descriptions. You get the interfacing. It's just a far more complex interface. And somehow, we've got to keep that simple, straightforward, while not constraining the flexibility that the domains need to communicate all that information. Okay? So, cool.